Hi, everybody. April 3rd, happy Friday. We're going to be discussing, this is lecture 29, we're going to be discussing section 8.8, applications of Taylor polynomials today and Monday, and you'll discuss them in recitation on Friday. All right, the meeting is going to be three parts. Marcy, grab one of these. Okay. So the first part of the meeting, if you came in late, make sure you grab one of the handouts. First thing I want to talk about is max versus sup versus bound. So I'm just going to do some examples. So consider the function f of x equals x squared. And on the interval from 2 to 4. So what's the max y value on that interval? $16, good. So it's f of 4. Which is 16. So you could think of this graph. So this graph goes through 2, 4, goes through 4, 16, and the max is achieved there. Now, what if I have the same function, and I have this as my interval? Maybe I'll, to get rid of confusion, I'll make the left endpoint be 1. So you're not thinking I'm talking about points in the graph. So 1, 1. Okay. So now what if my interval is now 1, 4 without the endpoints? What's the max y value on that interval? Somebody speak up because we got stuff to cover. What's the max y value? This is a concept from Calc 1. Yeah?
So limit as x approaches 4 of x squared.
Well, max y value is the maximum y value for all the x's in that set. There is none. The max y value is not 16 because 16 is not a y value for x's in that interval. You could say, well, maybe it's 15. Well, there are y values in this graph that are bigger than 15, so that 15 is not the max. Okay, you could say maybe 15.999999. Well, that's not the max because there are y values bigger than that in this set. What's the sup? The supremum. Supremum means what's the smallest value that's greater than or equal to anything in that set. Well, there is a number, 16, that's greater than or equal to every number in the set of y values on that other graph. This is not a number in that set of y values, but it's the smallest number that's bigger than any of those numbers, or greater than or equal to. Now, the sup in the previous example is also 16. Happens to be in the case of a closed interval, the sup is a y value that's actually achieved somewhere in that interval. But in the case of an open interval, the sup can be a y value that's not actually achieved. Okay, what if I tell you this? G of x equals cos x, and I give you this interval. What's the max? Don't know. What's the soup? Don't know. Well, Marcy, what were you going to say?
B squared.
Mm.
Oh wait, never mind, it's the wrong function.
You know, we don't know what this graph could look like. It could look like this. It could be a part of the graph that looks like this. In that case, there's not going to be a max. There would be a soup, but we don't know what it is. It could be that the graph looks like this. In that case, there would be a max. What would the max be? It's a cosine graph. 1. The height of that peak on a cosine graph would be 1. It could be the graph looks like this. What's the max then? Well, there's no max. There is a min in that case, but there's no max. In all these cases, though, there would be a soup. In this case, the soup would be this y value that's missing. In this case, the soup would be 1. In this case, the soup would be whichever of those y values was bigger. What's a bound on the y value? Marcy?
Is it like an asymptote?
No, a bound means a number that you're sure is greater than or equal to any number in the set. Kenzie?
So for cosine of x, it would be from -1 to 1.
No, a bound on so we're looking at it would be the number 1.
The upper bound would be 1, then the lower bound would be -1.
I just so bound just means upper bound, yeah. So you see the value in talking about a bound. So for instance, consider the heights of all the people at OU, all whatever 3,000 or so of people or 5,000 who are on campus today. Is there a max height? Yeah. Is there a soup height? Well, yeah, whatever the max height is, what is it? Okay, but quick, somebody give me a bound on the heights.
7 feet.
Oh, not sure. I mean, look at the basketball players. Not sure. I mean, 20 feet. There's never been a person higher than 20 feet. So the idea of bound is don't think too hard. Just pull out a number that you're sure is big enough. I mean, if you look at the Guinness Book of World Records, there was that tragic dude who was like 14 feet tall, right? And then he didn't live very long, but he was, and there are lots of basketball players over 7 feet. So you get the idea of the usefulness of a bound. Sometimes it's the only thing you can come up with, and sometimes, in the case of max heights of people at OU, it's just the fastest thing I can do. Otherwise, I'd have to query all the people at OU. So in these cases, I could use 16 as a bound here. 16 is a bound here. A bound could also be 17. I mean, 17 is greater than or equal to all the numbers in that set. So 17 is greater than or equal to all the numbers in that set. So there are cases when you can talk about a bound where you might not have a max. You might have a soup, but you don't know what it is. Okay, so that's meeting part 1. Max, soup, and bound. Meeting part 2 is this crazy handout that I gave you. Which I was really proud of last night, but then over breakfast I realized I needed to change all the soups to bounds. So if you look at your handout, page 3 and 4, I've crossed out the word soup in every instance, and I've put the word bound in its place. So now you'll appreciate, I hope, the significance of that. All right, I want to discuss this handout. Okay, so the first part of this handout, the first page, we actually have used before, this idea of the alternating series estimation theorem. So in this special case where we have an alternating series and whose terms are decreasing, or they never increase, and whose limits are, the limit of the terms is 0, then we know that that series will converge. Yeah?
Can you turn the lights down?
Yeah. This hurts to do this. Okay, so in the case of an alternating series that meets those requirements, we know the series converges. And if we can, this theorem is about this. If we define the term S to mean the whole series, or the sum of the whole series, and we define the nth partial sum to be the sum of the first n terms, and then the nth remainder to be the sum of all the remaining terms, so there's the nth partial sum, and there's the nth remainder. Clearly, these two things add up to the whole series. So S equals the nth partial sum plus the nth remainder. And if I subtract, then I get the nth remainder is equal to just the total series, the total sum, minus the nth partial sum. So the alternating series estimation theorem, A set, I just made that up, very clever, says this. There's a bound on the actual remainder. The bound is going to be less than or equal to this thing, which is just simply the very next term that you left out. Just look at the first term that got left out. Don't worry about this whole remainder. This whole tail is being added up. But we want to just get a worst case bound on it. We can just look at that very first term, and that's going to be an upper bound on the remainder. Okay, so we've actually used that theorem before. Now I want to talk about something from section 8.7. So today's topic is section 8.8, but we're going to be using tools from 8.7, which when we were discussing section 8.7, I promised you we wouldn't really use this. We didn't really in section 8.7, but now we're in section 8.8, and I get to break my promise. So we're going to be talking about Taylor polynomials. So, you know, here's a Taylor polynomial. It's not a Taylor series because it ends. It ends at the nth term. So there's a bunch of terms being added up, starting with the power k equals 0, starting with the power k equals 1. Well, this actually should be k equals 0. So cross that out. This should say k equals 0. Now, so notice that thing always converges because it's just a polynomial. It's just a finite bunch of things being added together. Now we can think about this. I've got some function that I want to that I use to build this Taylor polynomial. So the Taylor polynomial is t subscript n, and so it's not going to be the same as the function in general. So the question is, what's the difference? So this letter r in this setting is different from the letter r, the use of the letter r on the previous page. This is the difference between the function, the actual function, and this Taylor polynomial. The previous page, r was a difference between the whole series and an nth partial sum. Here, we're taking the difference between a function and the nth partial sum. And so if I do arithmetic, then the function actually equals the Taylor polynomial plus whatever this remainder is. Now it's subtle. Again, in the previous page, this remainder was the tail of the series. Here it might be something different. So we want to know if we approximate. We just want to know. We want to get an idea of how big that remainder is. How far off are we from the function if we use this Taylor polynomial? Well, so there's this puzzling formula called Taylor's formula, and it says this: if you have a function and it's known to have a bunch of derivatives up to n plus 1, and you build this nth Taylor polynomial, and then you can talk about the remainder. Well, here's what the theorem says. Given any x in some interval around a, where you have the Taylor polynomial around x equals a, the remainder is exactly this. Exactly. That's a big deal. So the remainder at some number x, like how far off you are by using the nth degree Taylor polynomial instead of using the function f. It's exactly this. So great, I got an exact value. But the thing is, this says the exact value is attained by doing this calculation. Find the n+1 derivative of f, and then there's just some special x somewhere that makes this true. So that's kind of like me telling you there's a pot of gold somewhere in Ohio. Well, great. I mean, in theory, that's great, but it doesn't really do you any good if I don't tell you where it is. So this is absolutely true, but it doesn't do you any good in its current form because it doesn't tell you where this z is going to occur. It's just going to occur somewhere in this interval, or somewhere in this interval, so somewhere in Ohio. Well, so the way we actually use this is we use it to get bounds. So that remainder is exactly true at one particular value of fn+1 of z. But if I'm just interested in what's the worst case of this, what's the bound on this, well, I could look at all of these things and I could take the biggest one, take the bound on that set. And then the actual remainder is going to be less than or equal to that thing. That's something I can compute. Another way that we use it sometimes is we actually that will give us an actual bound on a bound on the actual remainder at the x value x. Sometimes we and this should say the actual remainder for all x is less than this. Take the bound of all these possible derivatives and take the worst case of this. So this should say bound as well. Again, this looked really good last night. So those should say bound. So this is all this is a lot. This is dense writing even if it didn't have all this red ink on it. But I'm going to, meeting part 3 is we're going to use these. I'm going to show you how you use these in an actual problem. So that's meeting part 3. So example 1, just going to do one example. We're going to let f of x be square root of x. So this is similar to homework problem 8.8, number 9. It's not numbered that way in WebAssign. Well, it is in the fine print. So question A is, approximate that function by a Taylor polynomial of degree 2 around at the number a equals 9. So approximate f by a Taylor polynomial degree 2 at the number a equals 9. Okay, here we go. Remember, the definition of Taylor polynomial from this handout. The Taylor polynomial is going to be this baby. So we got to build one of these where n is the number 2. So we're going to use that definition from the handout. So let's make a table. Let's make a table with n, and then f parentheses n of x. So that means the nth derivative of that function. And then the next column is going to be f parentheses n at a. So that means the nth derivative at 9. And then the last thing is going to be the coefficient, c subscript n. So that's going to be f parentheses n at 9 over n factorial. So starting with n equals 0, well, the 0th derivative is just f of x. It means I don't take any derivatives. So then f of a is square root of 9, which is the number 3. And so c0 is going to be 3 over 0 factorial, which is 3 over 1, so that's the number 3. We got our first coefficient. Okay, n equals 1. That means we're going to find the first derivative. Remember from Calc 2, this is 1 over 2 square root of x. So f prime at 9 is going to be 1 over 2 square root of 9. So that's 1/6. So C1 is 1/6 divided by 1 factorial, so that's 1/6. Okay. 2. F double prime of x is going to be minus 1/4 x to the 3/2. That's on the bottom. Minus 1 over the quantity, 4x to the 3/2. So f double prime of 9 is going to be minus 1 over 4 times 9 to the 3/2. So that's minus 1 over 4 times 27. So that's minus 1 over 108. And so C2 is minus 1 over 108 divided by 2 factorial. Okay, well, 2 factorial is just the number 2. So this is minus 1 over 216. So we've got all the coefficients that we need. It turns out, though, we're going to need to use the next derivative. So I'm going to go one step farther, and I'm going to get the third derivative. F triple prime of x is going to be 3 over 8 x to the 5/2. Just using the power rule over and over again here. But we're not going to need to do this other stuff. Okay, so here we go. Let's build our Taylor polynomial. The second degree Taylor polynomial is, we'll just get those coefficients and park them next to powers of x minus a. So 3 plus 1/6 times x minus 9 minus 1 over 216, sorry, minus 1 over 216 times x minus 9 squared. So there's my second degree Taylor polynomial around a equals 9. And there we go. That's the end of part A. Part B. Use Taylor's formula to estimate the accuracy of the approximation the approximation is f of x is approximately equal to t2 of x. That is, instead of using square root of x, use this formula. 3 plus 1/6 x minus 9 minus 1 over 2/16 x minus 9 squared. So on the interval, between 9 and 9.5. So I'm not going to use this approximation for all x's. I'm just going to use it for x's in that range. Well, notice that our interval is I from 9 to 9.5. So we're going to use you can use your handout, and I'm going to pull up this handout on the board. It's a mess. So again, we want to get a bound on the actual remainder, and we're going to do it at a particular x value. We're not going to. So we're going to consider this the actual remainder at x. And so that's going to be less than or equal to the bound on this set. The set of these things. I got to look at the next derivative, n plus 1. So I got to look at the third derivative. So 3 over 8x to the 5 halves. 3 over 8x to the 5 halves for x in that interval. Well, I'm going to do it this way for x between, I'm going to say for z. Actually, and I should put z here because that's what's used in this formula. So I'm going to look at some z where z is between 9 and 9.5. And in that handout, that's a strict inequality. And then multiplied by absolute value of x minus 9 cubed and then divided by 3 factorial. Okay, now what's a bound on this set for z's in this interval? What's the biggest this can be? Marcy's got a hand up. There's some more hands up. Who can tell me what they think is a bound on the value of that when z is in that set? When z equals 9. Why 9? Why not 9.5? Yeah, this is the biggest when z is the smallest. Now notice, 9 is not in this set, but it could be used as the bound. So a bound for this would be 3 over 8 times 9 to the 5 halves, and then divided by 3 factorial, and this being multiplied by x minus 9 to the third power. So what this ends up being is 1 over 3888 times x minus 9 to the third. So that's the bound on the actual remainder at any particular x value. Now let's think about what's the worst remainder or the worst error committed anywhere. Well, for that we're going to use the next formula. We're going to figure out, again, sorry about this. I thought about just reprinting this. We're going to take the bound not only of that set, but also what's the worst that this can be. So that's going to be, oh my gosh. So the bound on the error anywhere on the interval, the overall bound, is going to be, I'm just going to denote that by r. So the bound on actual error everywhere, well, that's going to be that number, 1 over 3888 times whatever the bound is on this set, x minus 9 cubed, that's absolute value. And we have to take the bound over all the x's in that interval. So somebody tell me, what is the bound on this? Marcy, I'll call on you this time. Your hand's not up. But what do you think the bound is in this case?
Me?
Yeah, because your hand was up before, but I didn't call on you. What's the biggest this ever gets?
Biggest that would ever get is when x equals 9.5.
Exactly. In this case, it's at the right endpoint. So this is going to be 1 over 3888 times 0.5 cubed. And it turns out that this is 0.000032. There we go. That's the worst. That's a bound on, I don't know where it happens. I don't know if it ever gets that bad. But there's no x in that interval where the approximation is worse than that. Now, you have on your homeworks a question C. Actually, it's in the book as well. C, graph R, and this should be R3, the bound of, I'm sorry, so R2. Graph R3, R2 of x. Well, that's that formula over there. Absolute value of R2 of x. Well, we're going to graph y equals 1 over 3888 times x minus 9 cubed. And it's just got to be on the vicinity of x equals 9 for x's in that interval. So kind of running out of time. So, well, it's just going to be a cubic graph. All right, that's our first example of using these this Taylor remainder formula. Again, the Taylor remainder formula that's presented in the book is kind of a starting point, but you have to do things with it to actually, in practice, you start with that formula and then you put bounds on different things. Okay, let's do our quiz. Thank you, Gabriel.